turns out to be a metallic state, and we characterized it. We particularly calculated the conductivities. There, I will give you some overview over what is known about this system, and I will finish with a lot of open questions. Okay, good. So let me first say something about. Oops. Oh.
You can speak from here.
Okay. Yeah. All right. So about the people involved in this research. So there are like 5 people in our paper. So one is my PhD student, Zhao Chen. Another one is the postdoc, Zhou Yuxian. Then there is another postdoc, Yang Liu, she's actually from the particle physics group. A former postdoc, David Rodriguez Fernandez, who is now in Madrid as a faculty member, and me. So in this, again, I guess I don't need to say much about ADS-CFT to this audience. So I'll just skip this slide. Let me directly, give you some motivations for going to non-hermiticity. So why would we like to abandon the hermiticity requirement for the Hamiltonian? There's many reasons. The foremost reason is that in this way you can describe open quantum systems, right? So in quantum mechanics, the first assumption is that the system that you're describing is closed off to the outside world. There is no exchange of probability. And once you give this up, you have some environment that interacts with the system, then you will be able to describe open quantum systems, but this implies that the Hamiltonian starts becoming non-Hermitian. Condensed people actually studied these non-Hermitian situations for a long time. There's a huge amount of literature, and the main motivation in their case is that this allows for new transport phenomena. So one thing, for example, is the so-called non-Hermitian skin effect. I will not say much more about this, but roughly speaking, if you have a two-dimensional system, a two-dimensional non-Hermitian system, where you have, let's say, right-moving electrons or left-moving electrons, then if you take the adjoint of the Hamiltonian, this will exchange right and left movers. And so if the Hamiltonian is not Hermitian anymore, you might have more right movers than left movers. And so you have some current that goes in one direction. There's some current expectation value on the ground state. And it turns out that this current is actually localized on a boundary of a sample. Yeah. So this is the non-Hermitian skin effect. And this has been even observed in so-called these PT-symmetric non-Hermitian systems that I'm going to talk about. Another motivation could be if once you start breaking in holographic questions about quantum gravity, let's say black hole evaporation, you know that there is boundary unitarity typically, so there shouldn't be any black hole information paradox, and how to figure this out in the bulk up until like 13 years ago was an open question. Now we have some ideas about this, using the quantum extremal surface prescription and so on. But I don't think everything is completely settled here. And one way to understand better the situation, what's happening, is to kind of start breaking boundary unitarity or start breaking bulk unitarity and then see what happens. So I think this is also an interesting thing to do. And from the QFT side, you can actually go ahead and make non-Hermitian statistical physics models. Like this is a representation of a non-Hermitian SSH spin chain, Su-Schrieffer-Heger spin chain here. And the non-hermiticity comes from these like complex on-site interactions. And in this paper here, people showed, this is from the group of Calabrese in Trieste, they showed if you take the continuum limit, you get to a non-Hermitian 2D CFT. It's basically the BC ghost system with central charge -2 in this case. So by allowing for non-hermiticity, you are able to find new CFTs and new QFTs and maybe also new phenomena in QFTs. Okay, yeah.
Unitarity and validity in your mind, they are equivalent to each other.
Yes, I come to this in the next slide. Okay, good. So yeah, so let me give you some introduction. So let me remind you about some points concerning unitarity in quantum mechanics, right? So as I said before, in quantum mechanics, if you have a closed system, then you use the Schrödinger equation to describe this. And if the Hamiltonian is Hermitian, then the time evolution operator will be unitarity. So this is the answer to your question, yes? And so now what does this mean in particular? If you, in terms of your measurements, in quantum mechanics, you basically you fix some basis of projective measurements that you want to do, and then the probability of your state to be in a certain state I in this basis is given by the overlap with the wave function absolute value squared. And then you know that this is a probability distribution, so this is positive and summed up to 1. Okay, and this probability, you know, this condition here of that this is a probability distribution is conserved in time if and only if the Hamiltonian is Hermitian. You can quickly show. So basically, you start at some time 0, and then at some later time t, this is both is 1. The sum of all probabilities is 1 if and only if the Hamiltonian is Hermitian. Okay, good. So turning this argument around, if this is not true anymore, then the system might gain or lose probability with time through interactions with the environment. Okay, so this is the basic difference, you know, for open quantum systems. Good. So now there is a kind of a problem arising. So if you start out with most general non-Hermitian Hamiltonian, okay, then all hell breaks loose. Okay. So in particular, there are two things that happen. So, you know, in quantum mechanics, you always get a real energy spectrum, and that also comes from the fact that the Hamiltonian is Hermitian, so you can diagonalize it over a real set of eigenvalues here by this argument. So you take basically this equation, and then you take, you know, the static Schrödinger equation, and then you take the static Schrödinger equation for the bra vector. Then you take the adjoint of this, and you quickly find that E equals to E star if H equals to H dagger. Okay, good. However, it's much worse, actually. Turns out if H is not H dagger anymore, then H and H dagger might not even commute. And you might know this from your undergraduate math course. If H is a so-called normal matrix in matrix representation or normal operator, so H and H dagger commute, then you can show that H is diagonalizable. This is like the minimal requirement. Okay. If this is not the case anymore, then in the best situation, you can only bring H into some Jordan normal block form, something like this. Okay. So you don't even have a notion of proper eigenvalues anymore. Okay. So and this is where this PT symmetric requirement comes in. By imposing a parity and time reversal symmetry on the non-Hermitian Hamiltonian. So you allow the Hamiltonian to be non-Hermitian, but you impose that you should have some kind of parity and time reversal symmetry that commutes with the Hamiltonian. Then you can ensure that at least in some range of non-hermiticity, you still have a real energy spectrum. Okay, so it's some kind of weak version of breaking unitarity. Okay, so how does this work? Let's say you have your Hamiltonian is non-Hermitian, but it has a PT symmetry. Okay, then H and PT commute, so you can diagonalize them simultaneously, right? And then you can first pick, let's say, without restricting to anything, which pick lambda equals to 1, PT squares to 1, so the eigenvalues can be 1 or minus 1 here, and so we set lambda to 1. Then you see this, you see by the following argument that the energy spectrum is still real if PT symmetry is unbroken. Okay, so you first take this equation here. You first hit the wave function with the Hamiltonian, then with the PT operator. This gives you the energy eigenvalue. This is just a number, so it commutes with this operator here. But T is an anti-linear operation, so it involves complex conjugation, so you get E star in general. Okay, and if you do it the other way around, then PT acting on phi gives you 1 if you set lambda to 1. And then H acting on the remainder gives you the energy eigenvalue. Okay. So now you take the difference of these two equations, and by this equation, the left-hand side is 0 because you get the commutator. So if E equals to E star. Okay. So if PT symmetry is a symmetry, so it commutes with the Hamiltonian, the energy spectrum is still real, although the Hamiltonian might not necessarily be Hermitian anymore. Okay. On the other hand, if if the energy spectrum is not real anymore, then PT is broken just by inverting this conclusion. Okay, and this is a kind of a spontaneous breaking of PT symmetry. Okay, good. By the way, you can interrupt me with any questions anytime also.
Can I ask a question?
Yes.
Hey, Renee, it's Weijen here.
Hey.
So if you have a fermionic state, your t-square may not be 1, right?
If your fermionic state squared may not be 1.
Your t-square may not be 1. So do you allow that kind of state?
I haven't thought about fermionic wave functions. One probably has to go through the argument again in this case.
I see.
Yeah.
So far it's bosonic. I see.
Yeah, but you see, if you have a fermionic state, yeah, I mean, we can discuss this later. I haven't thought about it. Yeah.
Okay, sounds good.
Okay. Good. Yeah. Okay, so this is my general introduction. So why we need PT symmetry, or why we want to impose PT symmetry. Of course, you can also work with systems that don't have PT symmetry, but they are just non-Hermitian. But then it's you have to be careful to not do anything bad. Okay. Yeah. Okay, so like one of the main examples is this so-called PT symmetric anharmonic oscillator. In fact, all of this PT symmetric quantum mechanics business was kind of started in the early 90s by Carl Bender from the University of Missouri, and he is a mathematical physicist, and he first really investigated such problems. Okay, so this is a Hamiltonian here, where you start with normal p-squared term. It's just one single particle quantum mechanics. You start with a p-squared term, and then you have a potential which looks like the harmonic oscillator, but there is an additional ix to the epsilon piece, where epsilon is now real, and obviously this is not Hermitian anymore. Okay. But still it is PT symmetric because P changes X to minus X, and the T is complex conjugation, so it absorbs the additional sign in here. Okay, good. So what happens in this case is, and this is kind of an example for the generic situation, if you now start diagonalizing this Hamiltonian, I will not go into details. If you want to know how this is done, this involves, for example, defining the wave function on a complex contour in X space. So you also have to complexify your coordinates. Just look at the review papers of Carl Bender. There's a couple of review papers that are very nice. So what happens is, if epsilon is positive or 0, then you find that the spectrum is real. This is the spectrum here, and as a function of epsilon, and positive. And of course, for epsilon equals to 0, it's just a harmonic oscillator, right? So this is the PT symmetric situation, okay? The spectrum is real and positive, and everything is fine. And if epsilon is between 0 and -1, then it turns out that a finite number of these originally real eigenvalues here stay real, and an infinite number become. What basically happens is that these eigenvalues here, they start to coalesce pairwisely. They collide, and then they move off into the complex plane. So they form complex conjugate pairs. Okay, and in this phase here, PT symmetry is broken. Okay, by the argument that I presented before. So there is a finite number of real positive eigenvalues still left over, and an infinite number of complex conjugate pairs, because it turns out that this collision here happens closer and closer to epsilon equals to 0 if we are very high up in energy. Okay, and if for epsilon smaller or equal to -1, there's absolutely no real eigenvalues anymore. So the whole system and the whole spectrum has broken PT symmetry. Okay. Good. But in total here, if you look at the full spectrum, PT symmetry is broken below 0 here. But it's single particle quantum mechanics. If you fix some state, then you can say this state here, this pair of states is still PT symmetric, but up there it's broken. So it's a bit different from quantum field theory, right? So in quantum field theory, you always excite all the states in your spectrum, let's say at finite temperature, also here at finite temperature. So you're always in a PT broken phase. Good. Okay, so this is the generic situation. Usually you have some parameter, And in some parameter range, PT symmetry is preserved, and then in another parameter range, PT symmetry is broken. And you know, the place where these collisions happen is called an exceptional point. Good.
So in your second and third case,
Yeah.
building this system cannot be realized in nature, right?
In nature?
Yeah.
Oh no, it
Or
can.
in the lab,
Oh, it can. You can make a lot of open quantum systems that have at least approximate PT symmetry.
but the energy you say is not real. So how
No.
do you define energy?
Yeah, so basically what you have is you have some eigenstates. You can look at the literature. There's many systems, like if you have some quantum billiards where you have your billiard wall has some holes, and then there's probability in and outflow. You can realize these things,
Yeah, but in that case, how to say energy?
Oh, I guess you find in these situations what you do is you basically if you want to describe this from the point of view of the outside and the inside, then you have to do some more complicated description, something like Lindbladian description, and then where the BOF is somehow included. And then you integrate out the BOF, you get some effective Hamiltonian only for the inside, and this one doesn't have a real spectrum anymore. This is what people really do. Yeah. Yeah. Okay. Okay. However, this is a very good question because I will say something in a second here. What happens in the case where PT symmetry is broken, you have these complex conjugate pairs of eigenstates, which means that you always have some instability in the system because one of your energies has a positive imaginary part, right? So this is basically what you see in experiment. Also, they make these systems, they start breaking, PT symmetry, they start breaking unitarity slowly, and then at some point some instability kicks off and this thing is just running off. Okay, and so this broken PT phase can only be described by this PT symmetric ansatz for a certain amount of time. Basically, this is what happens. Yeah, good. Okay, yeah. So this is maybe the simplest PT symmetric system here, the PT symmetric qubit. So what you have is you have a two-level system with gain-loss balance. So gain-loss balance means the following. I have a Hamiltonian here, which is 2 by 2. There is some normal Hermitian entries, some energy E, and some transition probability between the two levels G. And then I add probability in one level, and I remove it from the other level, but at the same rate gamma. And this is the non-Hermitian system, okay? So this system turns out to be PT symmetric. This doesn't have space, this system, so P you have to define in some proper way, so that PT is a quantum number here. So this is the this is the definition of P and T. T is just complex conjugation, and P exchanges to two levels. And if you now go and diagonalize this, then you find the energy spectrum, which looks like this. And you see immediately if this if this inter-level transition probability G is larger than the gain loss rate gamma, then you're PT symmetric, your spectrum is real. And if G squared is gamma squared, these two eigenvalues collide. So this is the so-called exceptional point. And if G squared is smaller than gamma squared, you get a pair of complex conjugate eigenvalues. And in this phase, you're PT broken. Okay, good. Now, why am I telling you this? First of all, as I just said in answer to your question here, if you're in the PT broken phase, you always have one level with a positive imaginary energy, imaginary part, positive imaginary part of the energy here. And so this means that the system somehow is unstable, okay? Before everything is nice and stable. However, there's also an interesting thing that you can construct, namely the so-called Dyson map. So since these systems, if they are PT symmetric and also at the exceptional point, since they have a real energy spectrum, you can actually find a similarity transformation to a Hermitian system. And here it's pretty obvious. So you take the system with gamma equals to 0, and then you do a SU2 rotation where you complexified your parameter here, okay? And the complexified SU2 angle is given basically by the ratio of gamma over G. And if you do this similarity transformation, right? So this is some similarity transformation, and that's its inverse. then you can quickly show that you reproduce H by the Baker-Kaplan-Holzberg formula, for example. Okay, good. And this is the generic situation. So whenever you're in the PT symmetric phase, you have a real spectrum. Your formation is not unitary anymore. You know that in usual quantum mechanics, the similarity transformations that you know from classical mechanics become unitary transformations, but here this is not unitary. It's just that you sandwich with the transformation and its inverse. This is what you do. Okay, good. And the other important point, which allows us to generalize this to field theory, is that we use this. There's this complexified unitary transformation. So you start with some unitary transformation and you complexify it, and this turns out to be the generic case, because in the generic case, if you don't have additional symmetries around, there's always two eigenvalues coalescing and moving off to form complex conjugate pairs. And so on the spectrum or on the Hilbert space, you always have some SU2 transformations acting. Okay. In general, you can have more, you can have 3, 4, or n coalescing, but for that, you need additional symmetries protecting this kind of band touching. Okay, good. Okay, all right. So I will probably to skip this slide in view of time. What's the time, by the way? Okay, so I have half an hour, a bit more maybe, yeah. Okay. So now let's look at a PT symmetric field theoretic system here. So this uses the idea that we can use a complexified U1 rotation as Dyson map and get a PT symmetric non-Hermitian system from a normal Hermitian quantum field theory. So what you do is you start with a two-dimensional fermion. This is the Hamiltonian, and this is just the mass term. So n is the mass. And then, okay, it's kind of convenient to rewrite this mass term into basically, combinations of the original mass and the axial mass term. Okay, so you don't do anything here. The axial mass term just cancels out. Okay, under the condition that that these two prefactors are the same. Yeah. Yeah. And now you can act with a Dyson map constructed from the axial U1 charge. So this is the axial U1 charge. And you act with this not by e to the I theta q, but by e to the plus minus theta q. Okay. And if you do this, you can quickly show that that the prefactors here in front of these two terms start to become different. Okay. So here you get an e to the theta, and here you get an e to the minus theta. And so obviously this Hamiltonian is not Hermitian anymore. Okay. Not Hermitian, but it's still PT symmetric. And the P transformation is defined in this way here. Okay. So it's just e to the 2 imaginary part of theta times q for generic complexified theta times the normal parity transformation. Okay. And so in this way, you construct everything you need. You have a PT symmetry here, and the system is not Hermitian. And the important point is that this pattern here, this can be used in holography as well. Namely, you take some axial U1 rotation, and then you build your Dyson map by complexifying this axial U1 angle here, like by acting not with e to the I theta, but e to the plus and minus theta. Okay, good. All right. Okay, so now let me come to this non-Hermitian ADS-CFT model, which was originally devised by Landau and Abiyán. So they basically built this model on a holographic S-wave superconductor. I don't think I need to say much more about this here, so everybody knows how this looks like. I just say we will not look, or we haven't looked yet on the condensed solution, so I will just skip this. Okay. The important point is, of course, that we have some. In the scalar field asymptotics here, we have some sources, and these sources, there is a source for the field phi, for the autoparameter field phi, and another complex conjugated source for the complex conjugate field phi bar. Okay, good. So, and now what's happening is, when you want to do the PT symmetric deformation, you start out with this usual situation here, and you switch on a source. So this is just HHH with sources. And this means that you basically deform your CFT Hamiltonian by such a term But if m star equals to m bar, it's still Hermitian. Okay, and now you do a complexified U1 rotation on your field by an angle theta, so basically by a complexified angle I theta. Okay, and then your source changes like this, and the complex conjugate source changes like this. And so m star is not equal to m bar anymore. So you've basically achieved this deformation that I told you before. Okay, so the Dyson map is exactly this, and this then inserts these factors e to the plus minus theta here in this deformation term. Okay, and so this is where the non-hermiticity comes from. So this is what Avian and Landsteiner used. Yeah, good. So then the question is, what is the phase structure here? Okay. And this was partially worked out by them, but we added some things. So it turns out, if you look a bit careful at the holographic partition function, you do holographic renormalization as in the usual way. If you look a bit careful at the partition function, you find that it actually does not depend on, individually on these sources here anymore, but it actually only depends on the product of these two, and this is called n squared here. Okay, good. And so if n squared is positive, then this turns out to be the PT symmetric situation. I will say something in a second about this. And so in this situation, so you see if if the source times, so you see the source of the PT deformation times the complex conjugate source, it's still m bar. Okay, so the product of these two sources before PT deformation, where it was m bar, and after PT deformation are the same. So if PT symmetry is preserved, if this it turns out if this n squared is positive, you can always find a Dyson map between the unitary PT symmetric, the unitary situation, and the non-unitary PT symmetric deformation. Okay, so this is the outcome. I will show you the PT transformations in the holographic model on the next slide. So, and this happens if n squared is positive. If n squared is negative, however, so n squared is m bar, and in the Hermitian situation, m bar is m star. So this is absolute value of m squared. So it can never be negative. So if n squared is negative, you cannot make this Dyson map transformation back to the Hermitian situation. So this is a non-Hermitian Hamiltonian that cannot be mapped to a Hermitian one by a Dyson map, which means that PT symmetry is broken in this situation. Okay, good. And so the uncondensed phase structure with, where we only have these sources, but we don't go to low enough temperatures where we allow for an additional, expectation value being produced and so on and so on. The uncondensed phase structure here looks like this. So there is this n squared parameter here, and this can be positive here at 0 temperature, and then you're basically PT symmetric. It can be negative, then you're PT broken. And at 0, there's the so-called exceptional point. This is what Landsteiner and Avian found. And if you go to finite temperature, then it looks like then there is there are 3 phases. First, there's a phase 1 here, which is PT symmetric, that extends from positive n squared to 0. And this exceptional point now kind of fans up into some kind of quantum critical region here, which is also still PT symmetric. And then there is another phase 3 here, which is PT broken, which is just the finite temperature extension of this original 0 temperature PT broken phase. Okay, good. So this is the phase structure, and yeah. So
limit or backreaction.
This is fully backreacted. Fully backreacted. Yeah. Even at 0 temperature. So it's Landsteiner and Avian even wrote down some infrared fixed points here, for example. Okay. Yeah. Good. Yeah. So there's something interesting happening at t equals to 0 and n squared equals to 0. Actually, the geometry is still ADS. So the scalar decouples from the geometric part, even with this deformation. Okay. Yeah. So this is what happens, and here is a summary of the properties of these 3 phases, and I will go through them one by one in the next slides. So phase 1 is in some sense completely normal. The free energy is real. it's stable in the scalar channel, it's stable in the vector channel. And then since we switched on, although we don't allow condensation here, but we switched on some switched on some source, and hence we will generate some superfluid density that you can see in the, as a 1 over omega pole in the imaginary part of the conductivity, right? This is positive, and so everything is fine. Turns out that this deformation suppresses the quantum critical conductivity, so the analytic part of the real part of the conductivity becomes smaller as in the undeformed case. The sum rule holds, and the null energy condition in the bulk is preserved. Okay, so everything is fine. And now in phase 2, what happens is phase 2 is already a little bit funny here. It starts to becoming unstable in the scalar channel. The vector channel is still stable. This superfluid density starts changing from positive to negative. You get an enhancement of the quantum critical conductivity, and this is a implication from the sum rule, because the sum rule also still holds. And so if you here, in a sense, you kind of take away probability from this delta function in real part of sigma of omega, then you have to add it at omega equals to 0, for example. And NEC is violated in the bulk. And phase 3 is very weird. So you might have already noticed I wrote absolute value of temperature here. So the temperatures actually become complex in phase 3. I will say something about this later. So in phase 3, PT symmetry is broken. The free energy becomes complex. This basically has to do with the fact that the back-reacted geometry becomes complex and the temperature becomes complex and so on. It's unstable in the scalar sector, still stable in the vector sector. This superfluid density becomes complex. The whole conductivity becomes complex. I have no idea what this means. And the sum rule holds still, however, but NEC is ill-defined, right? Because, you cannot, and basically the field configurations and the metric in the bulk become complex. And then you cannot say that the expectation value, of the energy momentum tensor, contracted with some vector fields is positive or 0 if the energy momentum tensor becomes complex, right? Complex number, it cannot be either positive or negative or 0. It can take more values. So yeah. So this is the situation, what we know so far. So let me go through this one by one. And so first, let me just talk about the solution structure. So this is the full back reaction. PT symmetry acts on the solutions in the following way. So we take a gauge. Turns out that you can still do a gauge fixing that m and m bar are always real, but then m times m bar can change from positive to negative. And in the PT symmetric phase, at least you can get this change. You can do this gauge here, and then P acts in general on the system by exchanging phi and phi bar. Okay, so P acts by exchanging phi and phi bar. He also exchanges phi and phi bar because it involves complex conjugation, and then the solution structure is basically in the bulk is basically labeled by whether phi and phi bar is real, then it's PT symmetric, or phi and phi bar is not real anymore, then it's PT broken. Okay, good. So the boundary conditions of the field are as usual. We fix some certain convenient mass for the scalar here. The free energy is just what you get from holographic renormalization, and then you basically calculate the free energy and you find this kind of structure here. So let me first talk about the free energy. So in the PT symmetric case here, you start with one solution branch here, that has a real free energy. The dashed lines are the imaginary parts, they are 0 here. Then this goes through the exceptional point, goes on, stays real. The free energy stays real in phase 2, but another branch comes up from -infinity and merges with this one. And then you go to phase 3 here, and here you have two complex conjugate solutions where the free energies obtain complex conjugate eigenvalues. So this is what happens here. Okay, good. Any questions?
This solution metric is real or complex?
Here the metric is real. Here the metric is real. Here the metric is complex. In this phase 3, which is the final temperature version, and this was already observed by Landau also. Yeah, yeah. I don't have a good interpretation of this.
Complex metric mean.
Yeah. Yeah. This is a big issue.
Yeah, because they modify the boundary condition.
Yeah. So there is a paper by Witten recently that kind of classifies complex metrics from some years ago. We looked at it, and ours fall into the bad type, basically. So these ones are this doesn't seem to be a very good phase somehow. So I think it makes sense, in some sense, I would say it makes sense to look at kind of maybe an extended system where this doesn't happen so badly or something like this. Yeah, this might be an interesting future direction. Yeah, but yeah, this is the outcome basically. And how to say, in a sense, the fact that you get a free energy for two solutions that is complex conjugate kind of fits with the generic structure of the spectrum of PT symmetric systems, right? So yeah, so I as I said, there's some things in phase 3 I don't know what to make of them right now. Okay, good. So also the expectation value here for the operator follows the same pattern. In phase 1, is an expectation value that is real. Phase 2, you have two solutions. You have two real expectation values, and then in phase 3, it crosses over to two solutions with two complex conjugate expectation values. Okay, and so in phase 1 and 2, PT symmetry is preserved. Then there is some critical value of this deformation parameter over temperature, below which PT symmetry is broken. Okay. Yeah. Any further questions? Okay. So there's a little more to say about the thermodynamics. I already showed you these ones here. This is the energy density. I will not go through this right now in view of time. The temperature again is interesting. So for both phase 1 and phase 2, the temperatures are real, but then you have a complex conjugate pair of temperatures. This just comes from the fact that at some place if you try to define something like a horizon in the spectroreactive geometry, you have to put some Euclidean regularity condition, and the temperature just is complex. Yeah. Okay. Good. This is the outcome here. Good. So what about the stability? Ariane and Landau already showed that these systems are unstable in the scalar channel in phase 2 and phase 3. So you get some quasi-normal mode, which they call pseudo-diffusive mode, which at so X is their PT breaking parameter. The exceptional point is at 1. So if you're below 1 in the PT symmetric phase, everything is fine. And if you're above 1, then you develop a positive imaginary part. So there is some instability here. Okay. And yeah, and this instability is at low K. Okay, so it's it basically starts producing some additional expectation values, which however are homogeneous. Okay, good. Okay, so the question is, what is the endpoint of this instability? And the answer is it's not known. So this is, yeah, it's not known. Okay, so there is a second paper by Landau. Actually, we also tried for a long time to find the endpoint of this instability. Since this is in the scalar channel, the scalar field mixes with A0, so with the charge density, and so you could think that maybe the endpoint of this instability is a state where you kind of spontaneously produce charge density out of vacuum, but we couldn't. Yeah, so we couldn't find such a solution. Joey in particular tried very hard for a long time, and so it's unknown. And there is some other weird things happening. So these guys here, they try to do the following. They say, okay, we start quenching from phase 1 to phase 2, and from phase 1 to phase 3, for example. And the quenches from phase 1 to phase 3 happen in the following way. So this is the expectation value of the scalar operator. You quench into this phase, and the deeper you quench into this phase, the longer you stay into this phase, the expectation value starts growing exponentially. But at some point, at some time, you return to the original phase you started with. Okay, and so this I really don't know. I've never seen something like this before. Some phase where you really cannot quench into it. Yeah. So if you have some idea what this means, I would be very happy to discuss this. Yeah. Yeah. Good. Good. So it's unknown. What is the endpoint of this instability? Okay, so now let me come to the third part of my talk, which is basically our work, namely the conductivity and the sum rule. So we looked at the AC conductivity. So, you calculate the AC conductivity by doing linearized vector perturbations in the bulk. You do this at zero momentum because the AC conductivity is defined at zero momentum via this Kubo formula here. So what you have to do is you have to calculate basically the retarded two-point function of the current with itself. And this is in, this is in, encoded in the ratio of the subleading term versus the leading term here in the expansion of the perturbed vector field in the bulk. And so this is how you calculate this. You solve the perturbation equations with ingoing wave boundary conditions, and then you just take the ratio. And so at low frequencies, because basically, we have switched on this source for a complex field, we expect to have the typical structure for superfluid density appearing here. And this is what happens. So the rho s is the superfluid density. Q is the charge of the scalar operator. And then there is a delta function and a 1 over omega pole, and their coefficients are related by the conic relations as usual. Okay. So what you find for the conductivity is, if you do this in phase one here, you find that the real part of the conductivity is decreased as you start increasing the PT breaking. So this is the situation without PT breaking. This is just Schwarzschild. We haven't switched on a background charge density here, right? So this is just Schwarzschild. Then it goes down. So there's some depletion of basically the real part of sigma. And at the same time, the imaginary part of sigma here has this 1 over omega pole, and the delta function is also there in the real part that you cannot see in the numerical plot. And so, this is the structure in phase one. So everything is nice and looks kind of normal. Okay, you get some depletion of the critical conductivity. You get some induced superfluid density here by switching on this source for discharged operators. Looks all okay. If you go to phase two, this turns around. Suddenly, you get more quantum critical conductivity at low frequencies, and the superfluid density starts changing from positive to negative. Okay, this is what happens in phase two. And in phase three, all hell breaks loose. Both the real and the imaginary part of sigma, start developing a delta pole and a 1 over omega pole. This is just because the superfluid density becomes complex now, and the conductivity, also the analytic part, also becomes complex. Okay, and here I really have no idea what this is supposed to mean. Okay, I asked many Smarter colleagues; they also don't know. Good. So this is our results for the conductivity. Then we looked at the stability in the vector channel, because you need this to basically evaluate the sum rule. And it turns out that it's completely stable. So there's basically all vector quasi-normal modes have negative imaginary part in their frequencies. So these are the plots of basically the 1 over the determinant of the fluctuation operator in the fluctuation problem for the quasi-normal modes. And basically the quasi-normal modes are where the determinant vanishes here, and so this is where the poles are here, like this is where the white dots are. Okay, and so it turns out that the poles always in phase one, phase two, and phase three, they always stay in the lower half plane, so everything is fine. Okay, in the vector channel, and this implies that the so-called Farrell-Glover-Tinkham sum rule holds. So the Farrell-Glover-Tinkham sum rule is the following. So you take an integral over some very large frequency range of real part of sigma of omega. Now in holography, for this to converge, you have to kind of subtract the constant value that this real part of sigma takes at large frequency. So this is just some redefinition of the two-point function, of the retarded current two-point function. And then you take this integral, you send the cutoff to infinity, so this thing should go to 0. Okay, this is the sum rule. Okay, and there are some conditions for the sum rule to hold. which is basically that the retorted correlator has to be analytic in the upper half plane and on the real axis, and a certain fall off has to happen for this correlator at large frequencies, so that the real part of sigma basically goes to 1 at large frequencies. Okay, and so we basically ensured both of them. So this means that the sum rule is fulfilled, but nevertheless we checked, and numerically these are the plots, and we see for large cutoff frequencies it really goes to 0. Okay, so sum rule is there, everything is fine, and this is important for us because the sum rule is basically a consequence of causality. So Kramers coding kind of plays into this whole thing, and electric charge conservation, and so in a sense this system behaves normal in that sense. Okay, so electric charge conservation in particular is ensured here. Yeah. Good. So this is what we found.
What's the difference between unitarity and the causality?
Well, unitarity is unitarity. Causality is causality. You can have non-causal systems that are unitary, right?
Yes, it's in your setup, in particular in verse 3.
Yeah.
So the pretty symmetrical or broken?
It's broken. Broken. Like, for example, I guess systems, you can have weird systems. I have to look it up. Like, I'm thinking about flat band systems. Like flat band systems, I'm sure are not causal in the normal sense, you know.
Yeah, because
so
they have very rich and weird behavior.
Yeah.
Conceptual issues are hard to understand.
Are hard to understand here, that's true. Yeah, I mean, because usually we think of causality and unitarity being related in relativistic systems in some sense. Yeah, but now we are breaking unitarity. But I mean, I would say causality is I mean, this looks like causality is still there. So yeah.
Yeah, that's why I want to try to understand this.
Yeah. This is a very good point that one should look a bit more in detail, I guess. Probably there's some. There turns out there is very little account about PT symmetric non-Hermitian quantum field theories, but some things exist, like these fermionic systems or similar, versions of that, like QCD, that look like QCD, where you have a complexified axial mass term and so on and so on. These things exist, so there may be some discussion already, but I'm not aware right now out of my head. Yeah, good. Yeah, but you're right. This is a good point to look at this more carefully. Okay, good. So now this is my last slide before the conclusions. So in order to make sure that our results are not completely crazy, because they look very crazy, as you might hint at, yeah. We looked at the Landau-Ginzburg model, the so-called U1 rotor model. So this is basically Landau-Ginzburg theory for a complex scalar here, and so you basically could couple this to a source term, which in the usual situation is Hermitian if m bar is equals to m star. Yes, so there's a mass term, there is a phi to the fourth term, and then you can start deforming the system such that m bar is not equal to m star anymore. So you do exactly the same deformation. You solve the saddle point equations here. These are cubic equations. And then you can also find the superfluid density. This is all you can do. You cannot really calculate the conductivity here, because to calculate the conductivity, you need to look at fluctuations of the order parameter and also the coupling to electrons or something. In some underlying microscopic description. So it's not so easy to do here. Yeah. So we can look at the phase structure, and we can extract the superfluid density, and we find the following phase structure here. So these are cubic equations. So in general, there are 3 saddle points here. So this is first here, this phi s here, real part and imaginary part. These are the values of this field. And so in phase 1, when the deformation is weak, you find 3 fixed points here. So there is like one that is like ours in our holographic model that's on the real axis here. And then there are 2 complex conjugate ones, and that are not in the holographic model. And then if you go and you increase a little bit the strength of your coupling, you go to phase 2. and phase 2 is in yellow here. So this phase 1 fixed point that looks like from the holographic model now starts moving down the imaginary axis. This phase 2 fixed point comes up. So remember, originally in the holographic model we had some funny branch coming from infinity. This is now replaced by this one here, which is a fixed point that was not there before, but now it comes down from minus infinity here. These two collide and move off into the real direction. So these are the two relevant fixed points in phase 3. And this one up here doesn't do nothing. It's just some spectator, apparently. This just goes to the imaginary axis and starts moving. Okay. And so in the superfluid density, here we kind of qualitatively reproduce the phase structure. And here we qualitatively reproduce the behavior of rho S. So we have like this one phase here. This has real rho S. This moves down, and rho S stays real. The other fixed point comes over, they collide, and they move off to the complex plane, and then rho S becomes complex conjugate here. And this fixed point that comes in from here, this is again one of these branches that we didn't see in the holographic case. So in the holographic case, this branch comes all the way from minus infinity. And the other one just does nothing, just goes over there. So this is the structure, and it kind of qualitatively reproduces the holographic model up to this one spectator fixed point, okay? Yeah. So again, the full AC conductivity is not accessible in this model easily. You need to calculate the fluctuation effects, and you need to add some fundamental degrees of freedoms, like electrons, for example. This hasn't been done yet, okay? So this is all I have to say, so let me conclude. I guess it's very interesting to look at these non-Hermitian systems in ADS-CFT. There is some interesting phase structure with a quantum phase transition. There's some new behavior of the AC conductivity. The stability and the sum rule in the vector channel are guaranteed. And the phase structure and the zero frequency spectral weight is reproduced by our U1 rotor. This is our conclusion. And there's an outlook. Well, there's many open questions here. Some were already hinted at during the talk. So the stability and the nature of these phases in phases 2 and 3 remain kind of unclear. One could look at finite density, finite magnetic fields. One could look at superconductivity at low temperatures to go to the condensed phase. We are kind of looking at this right now. One could look at other transport coefficients. What does thermoelectric transport do, thermal transport, and so on. One could try to PT deform other holographic systems, or like find a better behaved version of this system in phases 2 and 3. And of course, it would be very nice to relate this to some strongly correlated PT symmetric systems that are already known to condensed matter physicists. There's a huge literature, and I think you better have a condensed matter friend to help you with this. Yeah. Okay, that's all I wanted to say. Thanks for your attention. Any questions? Questions from Zoom?
Hey, Renee, can I ask?
Yeah.
Question? So you mentioned that this type of system can always be, like non-Hermitian system can always be embedded to a system like with the environment, it becomes Hermitian. Is that right?
Well, I mean, it's not that it becomes Hermitian. I mean, what you do is usually you couple to the environment. And, you know, usually you describe the environment by itself as a Hermitian system, but then the coupling usually becomes non-Hermitian.
Yeah, so the dissipation is understood as caused by the coupling between the system and the environment. So how do I understand that from the Folk perspective?
Oh, this is a very good point. I mean, here we are working with this formulation where you've already integrated out the environment, right? So it's kind of not really visible here. So I don't have a good answer in this way, you know, to this question here. I mean, there is something. If you, I didn't really review this, but these guys here in this paper, they actually found a way to unitarize. So they found a way to construct this Dyson map to the unitary system by introducing an additional gauge field in the original system. But so basically what happens is that so the gauge field is used to implement the Dyson map as a gauge transformation. Okay, so this might help to understand this in a better way.
I see. Thanks.
Yeah. Thanks. Any?
If there's no more questions, let's ready again.
Thank you. Yeah. Okay. Somebody wrote in the chat. Okay, fine. Okay. All right.